Making external calls to untrusted addresses is the second most common exploit that leads to critical vulnerabilities and critical exploits, second only to Oracle manipulation, of course. So today, of course, we have to go over the 4 critical things that you must consider when you're looking at an untrusted external call. These are 4 things that you are literally always going to want to examine when you see an external call being made, and are more often than not going to lead to some significant vulnerability or bug or something like this. So of course, before we get to these 4 critical things and we dive into the video today, my name is Owen, and over around 2 years ago now, I founded Guardian Audits, and ever since then, we've uncovered literally hundreds of critical and high vulnerabilities in probably even almost 1,000 different smart contracts at this point, from doing dozens and dozens of smart contract security reviews and spending a couple thousand hours myself doing these security reviews. And my goal with the entire channel, and especially this video, is to distill down everything that I've seen along the way, all of my experiences from all of that time spent reviewing smart contracts, and give it to you so that you can ultimately become a much stronger blockchain engineer, security researcher, anything you're looking to be in a fraction of the time. All right, fantastic. So with that out of the way, let's get into these 4 critical things you must be factoring in when you're making external calls. All right, guys, amazing. So we're here, we're ready to go into the 4 critical things. I've got our whiteboard pulled up here, and we're going to deep dive into all 4 of the things. But first, of course, before we go through these 4 things, the main goal of what we're doing with this video, and of course, what we're doing with smart contract security in general, is to prevent all of these exploits from happening in the Web3 ecosystem. So with that being said, I'm going to ask you if there are any of these particular vulnerabilities and bugs that you didn't know about, or maybe you didn't think to check for, or a particular attack vector you weren't familiar with. Go ahead and write up a tweet on it and go and tweet it out and tag me in it or something so I can see that you did it. And this is going to do a couple of things. First of all, it's going to actually go and fully make sure that you understand the particular vulnerability at a deep level, enough to articulate it. And then second of all, it's going to make more people aware of the more esoteric things that we need to be looking out for when we're making external calls. And of course, that is the number 1 goal of what we're doing here, right? So as we're going through these 4 things, if something that you didn't know about, didn't think about comes up, write it down, make a tweet out of it, and go ahead and tweet it off. Could be a thread, could be a long form tweet, or anything like that. All right, with that out of the way, let's dive into these 4 pillars of things that you need to be checking for when you're making external calls, or when you're seeing external calls being made in a smart contract system. The first of which is, of course, going to be re-entrancy, right? So most of us will probably already be well familiar with re-entrancy. Now, what we might not be familiar with is all of the different buckets that re-entrancy can break into, right? So first of all, we've got just the classic re-entrancy, which is a single function that you're able to re-enter by, having an external call being made to an untrusted address. The untrusted address calls back into the contract, into the same function, right? So that is the canonical classic re-entrancy. Then we also have a cross-function re-entrancy, right? So pretty similar to the canonical re-entrancy, but instead of re-entering into the same function on a smart contract. So if we say we have our smart contract here, here's our system. If we've got our function, so let's say this is function foo, and that is way too big, so we'll make that a little smaller. So classic re-entrancy is, I'm an attacker, I call this. This calls my arbitrary address. Could be some contract here at my arbitrary address. This comes back and it calls foo again, right? And we re-enter into the same function, and that can be used depending on how the logic is in the foo function. We can manipulate the system that way. Cross-function re-entrancy is when we have another function, bar, of course, and what we do is we make this external call. Instead of calling into the same foo function, we come back here and we call into different bar function, but it's in the same contract, in the same system. So this can also have unintended consequences. And so to dive into specifically this one more, I would recommend you go check out our ultimate guide to reentrancy on this channel. It's a whole 40, maybe even 50-minute video that goes over all of these different reentrancy types that we're about to go over in excruciating detail with examples, and we see exactly what each of these is. But that is this idea of cross-function reentrancy. Well, now we can even abstract this out further, and we can talk about cross-contract reentrancy. Let's make that a little bigger. So now we're going cross-contract. So now, of course, as DeFi systems get more complex, instead of this system being a single contract, this system, if it's a very large and complex system, we could think of GMX v2, then there could be many contracts that are a part of this larger system. It's a weird contract. Okay. And so let's say that this line sort of denotes what's everything that's in our system, right? Now, a user might come and interact with the system, and there might be some sort of callback or something like this that can interact with an arbitrary address. So here's our arbitrary contract. Now, I might have called this function, this contract in the system, but what if, there's like this contract depends on the logic of this function or a function in this contract. Maybe it reads storage from this contract. There's all of these different connections throughout this set of contracts that make up the system, right? So what if my arbitrary contract here that got called through an external call that's happening right here, what if it calls into this contract down here? Well, this isn't the same contract that I initially interacted with, but it's still the same system. And if this contract is reading from the storage here, if we're able to manipulate the storage of this contract mid-transaction execution, well, that's another form of reentrancy that can potentially lead to a critical vulnerability. And so one system that is like this and even has exactly, this setup here is GMX v2. So they've got many, many contracts involved in the system. They have an exchange router, they have a deposit handler, a withdrawal handler, an order handler. All of these are different smart contracts, all within the same system. And they also make callbacks to arbitrary external addresses. And so we'll see after we go through all of these four things, I'm going to actually bring us through the GMX system, and I'm going to show us how we actually addressed all four of these individual reentrancy and the other three, which we're about to talk to, how all four of those things were addressed and how they actually do these callbacks safely, and more specifically, how they protect against this cross-contract reentrancy, which is a little bit harder to protect against. Okay, so that is classic reentrancy, cross-function reentrancy, cross-contract reentrancy. Let's talk about read-only reentrancy. Right? This is the most mystical of all of these types of reentrancy is read-only reentrancy, right? And this is when it is, so we are intra-system here. We're going to go inter-system. So not even within the same system, we're going to re-enter into a different system. So here's what this is going to look like. We've got one system here. It has sets of smart contracts. This is one system. And let's say it's relying on another system. So let's say this system is something like Curve. And let's say that this system up here, these people are going to be the people who get exploited. They're relying on some data in Curve, right? They're reading from Curve. Maybe they're reading the price of a pool from Curve or something like this. What can happen is I, as a malicious user, as an attacker, I call into this person's system, and then they have some sort of callback. So, in the middle of their transaction execution or something like this, ultimately, we're going to call my arbitrary external address, right? We're doing our external call, which is the point that this video is all about. This external call right here. Instead of re-entering into this system up here, we come here, we call into this system down here. And so what we can do is mid-transaction execution, we're executing some transaction with this system on the top. I've just now interacted with this system. I can change the data that is being read from this system down here, right? So I can manipulate whatever is going to be read while I get control of the transaction execution right here in whatever callback or whatever this might be, if we're sending some ether, some native ether, anything like this, right? And by way of manipulating the data that is returned from whatever this system is relying on, that is another way that can potentially cause a critical vulnerability to arise. And we've seen issues like this actually a couple now of these read-only reentrancy issues when we start to get more DeFi protocols integrating with one another. So that is read-only reentrancy. Now, there are a couple others such as, ERC 721 reentrancy or ERC 777 reentrancy, which have to do more with, using NFTs and you're doing a safe transfer, or if you're using a specific ERC 777 token, which makes an external call when you just transfer the token to the person who receives it or the person who sent it. If you want a deep dive on those types of reentrancy, highly recommend you go and watch the full reentrancy guide on this channel. We have examples and everything like that. So this is reentrancy. It buckets into these main types of reentrancy with, of course, some additional types, ERC 721, ERC 777, etc. But that is reentrancy. So that is pillar number 1 of what we need to be checking for on external calls. Let's talk about pillar number 2, which is DOS, the denial of service. So what is a DOS? Denial of service. What we're looking for is really just a way to make the transaction revert. If I can make the transaction revert, you can't use the system, right? And sometimes that can be critical if it causes a loss of funds, right? If you deposit and then I DOS the withdrawal, that means that the withdrawal always reverts. You cannot withdraw. You lost all the money that you deposited. So DOS attacks can be, in many cases, critical. So one of these core things we want to look to when we're making an external call is what is the potential to have this external call cause the transaction to revert. So first of all, if I'm making an external call to an untrusted address, well, they can just revert, right? They can just straight up revert and cause the external call to fail. Now, another thing that's a little bit more interesting than just having an untrusted address revert is something like a blacklist, right? So for making an external call to a token, to transfer a token like USDC, and we're trying to transfer that to a address that just so happens to be blacklisted for the USDC token, well, then that is also going to cause a denial of service, right? And so this is mainly something that will affect something like liquidations or, anywhere if you see some sort of fee being sent to an address, if that address is blacklisted, the transaction is going to fail. Now, a DOS can also happen if, for example, you are trying to send Ether to a contract that can't accept it, right? So if the contract does not have any sort of receive payable function or anything like that, then if you try to send Ether, it will actually revert and the contract will not accept the Ether. And so that is another way that we can get a denial of service. Another way to make this happen is if we're calling a function that does not exist. So if you have a contract, you're expecting a function to be there, you're going to call it, but that function doesn't exist on the contract. If there is no fallback function, or if the fallback function just reverts, then we will get a denial of service, right? It will revert. And then finally, an interesting one is the return values. So if I was expecting to receive a struct or, some data that could be decoded into a struct or, just maybe a Boolean or something like this, and I was going to decode the returned data into a Boolean or anything, I was expecting some sort of form of return data. Then, well, if the external call doesn't return what we expected and we're trying to decode that data and get the result, then that process of decoding the data, if it's not there or if it's just not correctly formatted for what we're expecting, that decoding could actually cause a revert itself. So return data not expected, that can also cause a revert and ultimately a DOS attack. So these are the main ways that a DOS attack can come about when we're making external calls. So that is the second pillar here of things to look out for when we're making external calls. Now, number 3, which is potentially the most interesting that I don't see a lot of folks talking about, is gas griefing. This is another thing we need to look out for when we're making arbitrary, untrusted external calls, right? If we are making an external call and forwarding all gas, then we're handing over the gas money of whoever's paying for the transaction, whoever's making the transaction, to this person, to this arbitrary, untrusted address, right? So, and really we would be forwarding 63 out of 64 of the total transaction gas because of the 63 out of 64 rule, which requires that 1/64th of the gas be left over and not forwarded to the external call, just to be able to ensure that there is at least some gas left over to finish the transaction. But often, if the untrusted address expends all of this gas, well, then you're only left with 1 out of 64 of the remaining gas. And sometimes that might not be enough to actually finish the execution of the function that's being called. So this could actually become a DOS attack. If I expend all of the gas that was forwarded to this external call, then we only have 1/64th of the total gas remaining. If that is not enough, then we have a DOS, right? We get an out of gas revert. Now, I mean, on top of that, even if we didn't get an out of gas revert, well, it still sucks to expend a ton of gas, right? What if I was calling this function, that arbitrary untrusted address, that's not something that I inputted, it's something that was configured by somebody else. If it's just an infinite loop and it just sucks up all the gas, even if the transaction can still go through, that sucks. I didn't want to pay for some while true loop, right? So, and that has a material economic effect on me and on the system because the transactions are going to be extremely expensive to interact with the system. And so this is another thing we need to look into is how much gas did we forward to the address? Is that untrusted address allowed to expend an abnormal amount of gas? Did we forward all of the gas, e.g. 63 out of 64 of the gas? And can they expend all of that, right? That is also a risk. So that is the crux of gas griefing and what this risk is when we're making external calls. Let's talk about the fourth pillar here, and then we'll go and we'll see how the GMX v2 system has addressed these, and we can see what it actually looks like to address each and one of these efficiently and effectively. So the final one here is going to be return values, right? So there are a few pieces to this. First of all, we have, the same note about unexpected return format, right? So this is the same thing as we put under DOS is if I return a format of data that you didn't even expect, or I didn't return you data, but you expected data, that is, in some cases when you're decoding, that's going to ultimately cause some sort of revert. Now, another potentially more interesting type of, exploit from these return values is itself another gas griefing type exploit. And it is especially dangerous because you cannot limit this by controlling how much gas is forwarded to the external call. So what can happen here is if I return something like a string, let's say, from an external call, or even just the bytes, if we just do a .call, it will automatically load the returned bytes into memory, whether you want it to or not. If we use a high-level .call instead of actually going to assembly, then all of the return data from the external call gets loaded into memory. And that can get quite expensive as allocating new memory is quadratically more expensive as you continue to add more and more. So I can limit an external call to only so much gas, say, like 1 million gas is the gas limit for that call. But if they return to me some huge string and I load that into memory, that's going to cost a ton of gas outside of even that external call, right? So that is completely uncapped by whatever you forwarded to the external call. That loading of string into memory is going to cost additional gas, and it could actually balloon up and be quite expensive. And so that is another form of gas griefing that can come up from return values. And then finally, just, unexpected values. So above and beyond the format, you might be expecting a certain set of expected values and ranges, but you could get returned anything, right? Literally any bytes could be returned from an external call, right? So you could, if you're expecting numbers 0 through 4, you could get 7 million, right? And that could be a number, or, you could get 17 or 32 or anything like this, right? So even just having completely unexpected values, never assume that an untrusted external call is going to return to you exactly the set of things that you expect, right? So that is the 4 pillars of the things that we want to be looking out for when we're making these external calls. Now let's go through each and every one of these and let's see how this is addressed in the GMX v2 system. So I've got the GMX synthetics code base here. This is the GMX v2 system, and we're going to go ahead and look at the callback directory. So they have this callback utils, and this is exactly where they are making these arbitrary, untrusted external calls, right? So with all of these risks, there is still a way to safely make arbitrary external calls, right? Even if they're completely untrusted, completely to any address, it could be any code, there is a way to safely make these calls, right? But we have to address all four of these things. So let's have a look at, for example, after order execution. So after an order is executed on the GMX v2 platform, there will be a callback to an arbitrary order.callback contract, which is configurable by the creator of the order, so the user, and we'll try to call this after order execution function on the callback contract. They're going to forward a limited amount of gas, and it's wrapped in a try catch. So let's go through, first of all, starting with re-entrancy. So GMX is the most prone system to re-entrancy as any, because it is a multi-contract system, right? So we have to worry about this potential of we enter into one contract. For example, here it would be the order handler contract would be the entry point for this execution. And then the callback gets made, and then we enter into a different contract, say the deposit handler or the exchange router or something like this. So how did GMX address this? Well, first of all, let's go to the order handler contract. So we can see if we look at the execute order function, which we'll find here, this is the function that will kick off the top level transaction that will ultimately call that callback as a part of the execution of the order at the end, right? So you'll see that we have this global non-reentrant modifier. So that is different than just a basic non-reentrant modifier, right? So normally non-reentrancy modifier prevents somebody from these first two types of reentrancy, classic reentrancy, cross-function reentrancy. The non-reentrant modifier just says you can't reenter into the same contract, right? If you entered into this contract, you cannot do this. At any time during this call, you cannot call into this contract again, right? Of course, that doesn't help us in cross-contract reentrancy scenarios where I'm not trying to reenter into this contract, I'm reentering into this one. And by way of changing the state in this one, I will change the way that this contract behaves. So that introduces the global non-reentrant modifier. So let's find where this modifier is declared, and we can see here is the definition of this global re-entrancy guard contract, which offers this modifier. So instead of setting a storage slot in this single contract here, we are instead pointing to a data store contract, which is independent, and setting the re-entrancy guard status for the entire protocol, the entire set of contracts with any call. So here's what this looks like. There is this data store contract, which is a part of the system, which as soon as I enter any contract in the system that has this global non-reentrant modifier, this will come here. It will talk to the data store contract. It will say, okay, somebody has re-entered, set the flag to true. Now, if I try to make this call into this, and I call another function that has this global non-reentrant modifier, it's going to come here. It's going to check the data store and say, data store, has somebody entered the system? Data store says yes. So we say, no, you cannot make this call. This call is going to revert because we are not allowing reentrancy into the system as a whole. So this is how GMX addressed this non-reentrant before with the global reentrancy guard contract. And you might say, well, this could probably be, addressed with just check-effects interactions. But specifically when systems get extremely large like this, there are many, many contracts in the GMX v2 system, and there's a lot going on here. And they've got all sorts of callbacks after order canceled, after order updated, after order executed, after deposit executed. They've got many callbacks. And so sometimes check effects interactions is not the easiest to actually support in a system that has many contracts and a lot of interactions. And so this global non-reentrancy is another solution to add on to using CEI as best as possible to protect the system here. So let us move on to denial of service, right? So let's go back to the callback utils. We're looking at our after order execution callback. We're making this external call right here. How do we protect against denial of service? Well, here we have a try catch wrapped around it, right? So if it fails, the execution of this transaction continues even though it failed. All we do is we emit an event that has the key and it has an order, and we continue on our merry way, right? It doesn't hold up the execution of the order, and that is good. So this is exactly how we address, if it just straight up reverts. We're not trying to send ether with this. A blacklist is, this is the same as just having it revert. Even if, there's something there that causes it to revert, then it continues. So we are good. Boom, boom, boom. If it doesn't exist, then try catch will just catch it. And there is no return data that we're parsing back. So boom, we're safe from DOS there. Let's move on to gas griefing. So first of all, you'll notice we are only forwarding the callback gas limit. And this is actually limited to, at maximum, it can be, I think, 1 million gas at this moment, right? So we have capped the most that can be forwarded to this call, and that's carefully monitored and controlled so that there's no amount of gas that could exceed the block gas limit to execute a single order or anything like this, which would effectively make an order unexecutable. And so this is exactly how we're protecting from any kind of gas griefing here, is that we're essentially we're limiting the callback gas limit. And then according to how big the callback gas limit is, the GMX keeper, which is the one executing these orders, takes an execution fee in proportion to that gas limit, as well as a few other things up front to cover any expenses that could possibly come from this external call. And so here we are safe from gas griefing. And now finally, return values. In this case here, we don't actually even have any return values, but I will show you a case where we are making an external call and we actually do carefully consider the return values. So we'll see here in the send native token function where we are using assembly actually to make this call. So what this would look like otherwise is, something like a payable receiver.call, and then we would return from this would be a bool success. And you might even just put it like that and leave it like that with, there's some value here, et cetera, et cetera, et cetera. So you might just leave it like this. Now this little comma here indicates that there is a bytes memory return data. Even if you put it there or not, it's being loaded in, right? So your return data is being loaded into memory. That is potentially, in some cases, if you make a call like this to an untrusted address, that could be potentially extremely costly in terms of gas. So to avoid loading that in, we do a low level call here where we send the gas limit to the receiver. Our out size is 0, right? So our out size is 0. That means we're not going to load in any return data into memory. We're not going to end up getting gas grief from this, right? And of course, we are not actually expecting any returns here, and we explicitly avoid that with the low level call. So this is how the GMX v2 system makes external calls to arbitrary untrusted addresses safely and avoids all 4 of these common pitfalls that come up when you're looking at external calls. So once again, if any of these were new to you, you hadn't considered these, or maybe, you weren't thinking about these, you didn't have them in your checklist before, then first of all, add them. Second of all, go ahead and make a tweet, write up, a thread or something like this on one of these that you maybe didn't know about so that other folks can learn about these, and tag me so that I can see that you did it. I'll give you a retweet or something like that. And let's spread this knowledge of these 4 different things that absolutely need to be considered whenever we see external calls being made. So with that being said, I hope that this video was valuable for you, and I hope that some of the stuff was new and you'll go ahead and apply this to your smart contract security reviews, your smart contract systems that you build in the future. And of course, finally, if you really love this security stuff and you want to join a community of folks who connect across the world, talk about security and share ideas, then of course you can go to lab.guardianaudits.com and you can apply to join our absolutely free community for smart contract security. And I can't wait to see you in there. All right, with that out of the way, I will see you in the next one.